Hi, today I'm going to talk about the Ridge regression, the Lasso, and principal component regression and partial least square regression. So first of all, I'm going to load the data in the RStudio, and I create a matrix contain all the data in X, and then all the data in Y, and then I have omit all the NAs in the Y in the dependent variables. So now I'm going to run the Ridge regression. So I'm going to using this function. So if we assign that alpha equals 0, then we are using the Ridge regression. Alpha equal 1 is the lasso. And then by default, the standardized is equal to true, so that the x variable, when we input the x variable into this function, everything will be in the same scale. So now let's define a sequence of lambda that we're going to use. Then we are going to run the Ridge regression. So let's say we are using like the 50. We have 100 lambda here. So let's say we're going to using the 50th lambda. Then and then um, here will be the coefficient when we use the 50 lambda for the Ridge regression. Okay, so now we are going to separate the data as into two set, train and test set, and then we are going to using cross validation to find out which is the best lambda to use for the Ridge regression. So you can see that the best lambda will be 200 and 211. So now we are going to use this lambda using to get the prediction on the test set. So you can see that our MSE is like 80,000. Then we can get the coefficient for the regression using the best lambda we get from using cross validation. Okay, so now we can apply the same procedure used on the lasso. So we define alpha equal to 1 as a lasso, and using the same sequence of lambda here. And then we are still using the cross validation on the train set and the test set to find out which one is the best lambda for lasso. So we can take a look. The best lambda now will be the 16th. Okay, so now we can predict the y on the test set using the best lambda in the lasso. So we can see that our MSE will be 100,000, where compared to Ridgid regression we have 80. So it seems like Ridgid regression is doing a better job here, but there's more parameter to we can change the parameter and then make it both make the result better. So we have to keep trying on different lambda or using different method. So one thing we have to point out is that on the Ridgid regression, the coefficient for some of the insignificant coefficient can be very small. However, in the Lasso regression, we can actually get the from RStudio. We can actually see that it returns that for some of the coefficient it can be 0. So as the coefficient shrink to 0, then we can eliminate those variables. It depends on different situations. So in this situation, we can eliminate some of the variables that equal to 0. So we can say that those variables are insignificant. So here are the variables that we are going to use to predict the y variable. So yeah, so basically for Ridgid and Lasso regression, the procedure is something like we first separate the test and train set, and then using a sequence of lambda to find out the best lambda for either Ridge or Lasso regression. Then we predict using the model that we get using the best lambda, and then predict the y using the test set. And then we can and then we input all the entire data set, and then we can find out the coefficient for the Lasso or the Ridgid regression. Okay, so now moving to principal component regression. We're using the library PLS, and then so principal component regression. Actually, for a very long time, this has been one of my favorite algorithm. But it really depends on the situation and the data. So apply all the method wisely. Depends on your situation. So there isn't always a best algorithm. So you should always try different algorithm to get a better result, but not the best result. So here we are applying principal component regression. So we can see that for using we are using cross validation here. So we can find out that using the cross validation, we can find out we can find the lowest MSE on using a specific number of component here. I'm not going to find that, and then actually you can plot that you can make that in a plot. So it seems like a 16 or 17 has the lowest MSE here. So yeah, actually 16 I think has the lowest MSE. But if you look at the variance, the percentage of variance explained, you can see that if you are only let's say if we are only interested for 80% of the x can be 84% of the x can be explained by using only the first 5 components. So we can actually, so if we are satisfied with the 80%, then we can just use first 5 component. So for the principal component analysis, basically we are just reducing 19 dimension down to 5 if we are satisfied with 84% of x explained. So if you want like 90%, then you probably want to go up to the first 7 principal component. So now let's say we are now let's use the cross validation and on the train set. So it seems like let's find out. It seems like the 8th or the 9th has the lowest MSE. But let's say if we are interested in like 80% of x explained, then probably we can just use top 5 component. And then we can see that the MSE is like 90,000. So which is better than Lasso, but still not good enough compared to Ridgid regression. So we can see that while using 5 component analysis, 84% of x is explained by the first 5 components, but for y only 50% of y can be explained. So you should always change the number of components based on your the condition that you favor. Let's say, so if you want the lowest MSE, then probably go with the 8. But if you want if you want to reduce dimension then you can probably use 5. Let's say if you are satisfied with 80%. So the same situation for the partial least squares. We can see that let's say it seems like the 4th component has the lowest MSE. But look into the percentage of variance explained, we can see that the first 6 components explain 80% of the x variable, and also explains 63% of the y variable. So instead of using the lowest MSE on the 4th component, we use I want to use the first six component. So we can see that the MSE will be on the test set will be 95,000. So it seems like in this video, it seems like the Ridge regression has the lowest MSE. However, Ridge regression use all the variables, all the x variables to predict y. So as you increase the number of x, then you're definitely going to get a lowest MSE. However, some of the variables can be insignificant. Let's say, so for example, in the lasso, we can see that some of the coefficient for the variables shrink down to 0. So it seems like we can actually remove some of the variables. Every time it should be on, depends on your situation. So in this situation, we can remove some of the variable that the coefficient equal to 0. So without using the other variables, we are definitely increasing the MSE, but we can also simplify the regression and also find out what are the variables that are significant to predict the y. The same thing also for principal component regression and the partial least squares. We are using this dimension reduction method to reduce the dimension from 19 variable or 19 dimension down to 5, 6, or 8 in this video that we use in the function. So one thing I want to point out is that each component is a linear. For a linear principal component, each component is a linear combination of the x variables. So in the first component can be rewrite as a linear combination of all the 19 variables. So all the 19 components are not represented by 19 variables. Each component contains some of the variance in all 19 variables. So no matter which, in the regression, we are only using 7 or let's say 6. We're using 6 terms for running the regression, but each component still contains some of the variance in all 19 variables. So don't get confused with between principal component to the variables, although they have the same number, but there's a mathematical ways to calculate, to rewrite each component in the form of a linear combination of 19 variables. So these are the function or the commands in R allows you to use Ridgid regression, lasso, principal component analysis, regression, and partial least squares. So each of them has their own advantage, and so you can use different method to see to test it out, whether you want to get the lowest MSE or the more you want to reduce dimension, or whether you want to increase the variance explained on predicting y. So thank you very much for watching. If you have any question, feel free to ask in the comment section. Thank you very much.